Alrighty. So we are live. I am live. I don't know why I referred to myself in the first person plural. Hey. Okay, let's see. Okay, awesome. We got questions right out of the gate. The first thing, just by way of announcement, so I just an FYI, there is this schedule conflicts thing. I have to drop my kids off at a thing that's literally like 5 minutes from our house. But I just have to actually like physically go and do it. So at 5:15 I will be AFK until about 5:30. But I will make up the gap in time that we'll lose. I'll stay that much later, so we won't be gypped out of any office hours. Usually office hours are kind of slow at that moment anyway, but I just want to let everyone know that I'm going to be dipping at 5:15. I'll be back about 15 minutes later. Okay, that being said, let's start hitting the problem. So second to last question on lab exercise 3. Okay, before I even dive any further into that, let me take a look at lab exercise 3. Let's see, let's throw this right here, put that right there. Okay, lab exercise 3, second to last question. Alright, so let's see. How do you quantitatively explain a greater reaction rate in pure O2 than house air? Okay, so let me see. I'm just looking at the question really quick. Many of the reactions you observed went faster and longer. Quantitatively. Okay, Kate, great question. All right. So when we are talking about reaction rates, right, I believe they might even say a little bit about this. Okay. So when we talk about reaction rates, what we're really talking about, whoa, that's a giant eraser. When we talk about reaction rates, what we're talking about are, we're talking about speed, right? We're talking about how fast a reaction goes. Right? That's what we're talking about with reaction rates. Now, in this question, they ask us to explain why the rate is faster in pure oxygen than air. All right? And so we have the rate of air versus the rate of just pure O2. And and the reaction rate in air is slower. The rate in pure O2 is fast, and they want us to explain quantitatively the difference. Now, air is about 22% oxygen. The air that we're breathing in and out right now, about 22% of it is O2, whereas oxygen is 100% O2. So the reason why it's faster is because pure oxygen is more concentrated. Air, in a sample of air, it's less concentrated, which makes it slower. Well, let's see, I'm going to need to scoot this down a little bit. It's less concentrated, which makes the reaction slower. So that is the quantitative difference. It's that 22% of oxygen in air versus 100% of oxygen in oxygen. All right, Carenza, let's see. In question 2 of lab 3, it mentions the surface of the hydrogen peroxide solution in the general bottle. Okay, let's see. Let me look at question 2. This experiment, it is important that the tip of the funnel be below the surface of the hydrogen peroxide solution in the generation bottle. Okay, give me a second. Yes, okay. Okay, so, here, hang on. Okay, so in question 2, lab 3, it mentions surface of the hydrogen peroxide solution in the general bottle. Confused because I thought the bottle was water. Okay, so. Carenza, so in the generation bottle, a stopper up in here. Then we've got this solution. This solution right here is hydrogen peroxide dissolved in water. So the hydrogen peroxide is what's called the solute, and the water is called the solvent, and together the solute and the solvent are a solution. So they refer to it in question 2 as the hydrogen peroxide because that was the solute in the solution, but the solvent of that solution is water, so it is an aqueous solution. It's a solution of water with hydrogen peroxide dissolved in it. When you look at the setup, so we've got this funnel that we use to add the stuff. So this right here is the funnel. And so this down here, this would be the funnel tip. The funnel tip would be right down there. And so to be below the hydrogen peroxide solution would be just as I've kind of drawn and colored it in here. You can see that the right here. This is the surface of the solution. With the tip of the funnel being beneath the surface of the solution. Right. Totally. So I realize that angles in the videos may not show everything, but this is to kind of illustrate. And then there's a second piece of tubing right here that goes, oops, and snakes underneath kind of this this is the collection container. Excuse me. It goes up and into there, and this is all filled with water, and this is filled with water, and then the bubbles come through here and are collected in the container. Excuse me. Okay, so that's how it's below. The oxygen is being collected. Do we keep the bottle facing up so the water doesn't spill out? Actually, no. So, so this is the collection bottle right here. Oh, I'm like, what happened to my thing? It got... This is the collection bottle, which is kept facing down, but you'll notice it's below the surface of the water. So it does, the water doesn't actually spill out because it's below the surface of the water. And then, okay, sorry, I see I've got a bunch of questions, but I'm answering Corinne's stream, and then I'll circle back. The collection bottle is initially filled with water. That way, 100% of the gas inside is pure oxygen, not air. If that makes sense. Okay. And then, so if the tip of the funnel was above the surface, oxygen would escape. If the tip was above the surface, oxygen would escape up the funnel, or I should say, some oxygen would escape up the funnel, rather than going to the collection jar. Okay. All right, Corinne, I'm going to push pause and go back. Okay, Prarthana, you've got a question. I didn't understand question 1. question 1 in lab 3, just to make sure. From what you observed. So let me know, Parthana, if you're talking about question 1 in lab 3. Okay, Kate. Oh, okay, Parthana. Okay, yes, okay. Gotcha. Okay, so let me take a look. Question 1, lab 3, from what you observed in the oxygen generation process of this experiment, what evidence is there that oxygen is not very soluble in water? So the thing to remember, so this is question 1, lab 3. So the thing to remember is this. Soluble means it can dissolve. Right? Soluble means it can dissolve. So if you add, for example, if you add sugar to water, the water dissolves the sugar. That means, right, you've got a jar of water and you have, a spoonful of sugar. Right, there's the sugar. Here's the water. When you dump the sugar into water, when it dissolves, what does the water look like? Here, it just looks like water, right? You do not see the sugar because it is dissolved. All right. Now, here is my question for you that will lead you to the answer to your question. So, Parthana, here's my question to you about question 1. In this experiment, do you see oxygen? Do you see oxygen? Or does it dissolve in water? All right, so hopefully that will lead you in the right direction. Oh, you got it, oh yeah, no worries.
See, man, love you.
Oh, dude, love you too.
Have a good time.
Yeah.
Good luck with the class.
Thank you. Catch you next
Uncle
time.
Jared says, what's up?
Oh, I will. Yes, I will.
Yes.
You can go back and watch the office hours later if you want to. My nephew was spending the night with for a couple nights with my kids, and he was just grabbing his stuff. He just left, and he said, "Tell them Uncle Jared says what's up," and I told him I would, and he says, "No, you won't. You won't actually." And I said, "Yes, I will. Go back and watch the YouTube video." So now I did. Okay. All right, let's see. Okay, no, the question is, why doesn't the water run out of the collecting bottle? Okay, we must be looking at different questions. Let's see. Okay, let's see. Let me try to find. Do. Sorry, I'm still trying to find the. Oh, okay, sorry. Perthon, I see the question. Why doesn't the water run out of the collecting bottle? Oh, so I guess this would be. I didn't answer question 1. I answered question number 2. Okay, so question 1 says, why doesn't the water run out of the collecting bottle when you invert it? Invert the bottle and remove the glass plate under the water. Okay, I'm tracking. So that has to, okay. So let's set the stage here with the actual question number 1. So here, you have a collection bottle that's totally filled with water. All right, so you've got water, you've got the bottle, and then you put this glass plate on top, all right? And then you've got this tray that's also filled with water. All right, and then what we do is you invert the glass bottle into the tray with the top of it submerged. All right, and then you remove the glass plate so that you just have this whole thing with water, but then also you've got all of this filled with water. And the question is, why doesn't the water spill out? And it's true that the water, the reason why the water doesn't split out has to do with, oh, let's see, a different color. With the atmospheric pressure is pressing down on the surface of the water, on the water's surface. That is what keeps the water in place. All right, so so that is why after you invert it, put that thing underneath, remove the glass plate, the water doesn't come spilling out of the collection flask because you've got the atmospheric pressure pushing down on the surface of the water, keeping all that water in the collection bottle trapped up in there. Okay, let's see. So, Okay, Kate, when I turned in my lab quiz, immediately saw the score I got. Don't understand why, because there were some free responses. I'm assuming that you'll have to... Oh, no worries. Yeah, Kate. Kate Weber. I grade all the free responses after the assignment due date. So that'll be coming in the near future. All right. Oh, Brianna, you already knew that. Okay. Let's see. Okay. So also, when the oxygen is done being collected, do we keep the bottle facing up so the water doesn't spill? Kate. All right. Here, Karen's. I'll get to yours in just a second. This is just a quick. So your current score is the score is your current score is the points scored before receiving any points for the free response questions. Essentially, I will go back and assign points for correct answers, which are added to the points you already have. Let's see. Okay. Yes. Oh, of course, Kate, you are welcome. So at Karen's, sorry, this is a ways back. Yes. Also, oxygen is more dense than air, so we don't need to worry about it flying away. All right, let's see. Okay, Esther. Thank you for being patient. Under the burning wood section of Lab 3, number 1 and 2. Okay, let me scroll over to that section. Burning wood. Number 1 and 2. It asks for time it takes to burn, but in the video, the time it takes for the splint to burn is not measured. Yes, totally. What I would say is, if they show the entire combustion on the video, you can time it. If they cut it off short, then don't worry about it. Okay, Susan, let's see. Number 1, question 7 on the... Okay. That's weird because I thought I fixed that yesterday, but it could be... So you're saying, sorry, that the question 7 on the extra credit still isn't showing up. I can check that. There we go. You know what? Yeah. No worries. Let me see. Okay, so Susan, so it could be so here's the deal. So on the extra credit assignment, number 7. So what was the initial problem is a couple of the answers I had uploaded images as the answers instead of just writing text, and I corrected that to using text, which should be able to be read by everyone. But it, like you're saying that you can't see it, and you're not alone. So what may be happening is the edits that have been made. I don't know, and I need to do a little digging on Canvas. You may, even though I'm able to edit it, it may not show up since I edited a live quiz. It may not show up till after the quiz closes. So, and I've got to do a little bit of digging, but don't stress about it because for number 7 on the extra credit assignment, I am after it closes. I'm just going to give everyone full credit on that problem. And I'll just be leery in the future of trying to upload images to into the choices on Canvas. I'll keep it to just the rich text editor. Okay, let's see. Can I show an example of converting grams per milliliters to kilograms per liters? Ah, interesting. Can I give an example? Let me see, extra credit number 12. Oh, hang on. I sure can do a problem like that. And, oh, you're getting an answer, a huge answer. I'm not sure if it's right. Okay, so that last part, I'm not sure if it's right either. And I can't tell you if it's right because the assignment is live, but I can totally do an example like that. Okay, so let's start hitting these one at a time. Okay, we did Q7. 2, can I show an example of converting grams per milliliter? I sure can. So let's see. So let's do a problem. Let's convert 14 grams per mil to kilograms per liter. All right, this one's going to be a little funky because we've got to do two things. We've got to convert our numerator, both our numerator and denominator. let's see. It says our stream status is poor here. Let me make sure I'm on the right network. Okay, well, let's just keep going. Or let's see. Maybe there's something I can do. Stream health is excellent. Not receiving enough feedback. Okay, well let's just see if we're able to power through here. Okay, so sorry, I got a error warning from YouTube. Hopefully, it's not buffering too horribly for you guys. Okay, let's convert this from grams per milliliter to kilograms per liter. Well, first, let's start by looking at our numerators, all right? So we want a unit conversion that is going to cancel grams, so I'll put that into the denominator, and leave us with kilograms, all right? Now, kilo means 1,000, so there is 1,000 grams in 1 kilogram, all right? 10 to the third. So grams will cancel grams, leaving us with kilograms. Now let's look at our denominator. We want to convert from milliliters to liters in the denominator. So if we want to cancel milliliters here, we need to put it in the numerator over here. Then liters go in the denominator. Now, 1 liter is 10 to the negative 3 milliliters. Wait a minute. Okay. So milliliters cancel. Oh, wait. Sorry, I messed that up. I messed this up. Hang on. So, sorry. 1 milliliter is 10 to the negative third liters. All right, now milliliters cancel. And you'll notice that as of right now, our units are liters in the denominator, kilograms in the numerator. So we're good to go. We have all the right unit conversions in place. And now we just multiply it through. And when we do, my calculator is telling me that my answer is 14. 14 starts with 2 sig figs. We end with 2 sig figs, and our units here are kilograms per liter. So it turns out 14 grams per milliliter is 13 kilograms per 14 kilograms per liter. Oh, you know what? It's saying I'm disconnected. Hang on. I'm experiencing some technical difficulties. Alrighty. Here, hang on 1 second. Hang on 1 second. I'm running into some technical difficulties. I just need to restart my secondary computer. Our stream's still intact, but I just lost the chat feed. So give me just 1 second as I reboot this thing. That is a 2-year-old. I don't know if you could hear the fussing in the background. Okay, here we go. Sorry, I'm just grabbing all my screens. Let's close that. Okay. Okay, I am back-ish. I just gotta log back onto Canvas. Okay. All right. Thank you for bearing with me. Okay, I'm still on Susan's. So, okay, we need an example of question 12. Since I gotta finish this Canvas login. Okay. All right, number 12. Okay. Let's take a look at number 12. Okay, so I can't do the exact copy of number 12, but I can do something similar. So let me grab a different metal. No, not the density of lead, the density of lead. All right. So lead. Oops. Let's do an example here. So lead, whose formula or symbol, sorry, is Pb, has a density of 11.34 grams per milliliter. All right, and number 12. What mass of lead would occupy 4.9 liters of space? All right, what mass of lead would occupy that much space? Hang on 1 second, I'm pulling up a calculator because I don't have a physical one on me. All right, so Susan, first thing that you always want to do, always start with identifying what you're trying to find. All right, and we are trying to find the mass of lead. All right. Now let's look at what we're given. In this problem, we're told the volume of lead. Volume of lead is 4.9 liters. We're also given the density of lead is 11.34 grams per milliliter. Now, we know that anytime you're given a quantity that's associated with a chemical equation, you want to write that equation out, because that equation gives you a roadmap to solve this problem. We know that density is equal to mass over volume, and we have been given volume, we've been given density. This will allow us to solve for our mass of lead. All right, so we're going to use this equation to solve for our mass. Density is equal to mass over volume. We're going to start by multiplying both sides by our volume so that we can isolate mass on one side of the equation. So we get a new expression which says mass is equal to density times volume. But now you'll notice when we plug in our values, density is 11.34 grams per milliliter. And our volume is 4.9 liters. We have a problem. Milliliters and liters have different units. They have different units, so we need to do a unit conversion before we can solve this problem. All right, so it doesn't matter which one you choose to convert. It'll be the same either way. I'm going to convert liters to milliliters. Liters in the denominator, milliliters in the numerator. 1 milliliter is 10 to the negative third liters. So now liters cancel. And 4.9 liters is 4,900 milliliters, and this is a number we can use. So mass is equal to 11.34 grams per milliliter times 4,900 milliliters. Now our volume units cancel, and now we can plug this in to a calculator or spreadsheet as I'm using. So 11.34 times 4,900. So our value here, the value that the calculator is giving me is quite large. It is 55566. But we can only keep two significant figures because our volume only has two sig figs. So the mass of lead that occupies 4.9 liters is 56 excuse me, 1,000 grams. And that is the answer to this problem. All the steps involved here are exactly the same as that problem on extra credit, number 12. But this one is, it's different numbers, different values, different metals, etc. Cool. Okay. Okay, so those, okay. Oh wow, I've got some catching up to do. Okay, so Susan, those are the answers to your first three questions. There will be more coming. All right, Carenza, let's see. If we don't need to worry about the oxygen flying away, why does she keep the glass on it? So, Carenza, kept the glass on it, just to be on the safe side. Okay. Okay, Prarthana. Yep. Okay. Let's see. Okay, Brianna. Okay, finally, I'm down to yours. Homework 2. There's a question that is completely blank of answers. Okay. I wonder if there's more images involved. Let's take a flight to the magical land of homework number 2. There we go. Question 7. I bet it's the same thing. Oh, yeah. Okay, Brianna. I'm learning this lesson the hard and slow way. Make a note. Oops. Okay. Let's see. Okay. All right. Okay. So that is Brianna. That is your question. You are welcome. Okay. Crimson, burning wood, part 1. She pulls the splint out of the jar without letting it continue to burn. She forces it to stop burning. I would just write under the okay. Let's see. Let's see. Okay. Okay, Susan. With your previous conversion, wouldn't you divide by 1,000? Okay, let's take a look. Okay, so Susan, let's take a look at there we go. Let's take a look at the conversion. Oops. So let's walk through this one step at a time. So first, we're just going to look at the grams. All right. So to convert from grams to kilograms, grams has to go in the denominator, kilograms has to go in the top, right? So 1 kilogram is 1,000 grams. Next, we got to set up the milliliters. Milliliters up top, liters down below. 1 milliliter is 10 to the negative third liters. Now, when you multiply this all together, all right, this is literally 14 is our only thing in the numerator. That's not a unit, right? Units wise, we've got kilograms in the numerator, liters in the denominator. But then numerically in the denominator, you have 1,000 times 10 to the negative 3. All right, and what I want to do is I want to zero in on this. 1,000 times 10 to the negative 3 is equal to 1,000 is actually 10 to the third times 10 to the negative 3. This is the same as 10 to the third minus 3, which is the same thing as 10 to the 0, which is the same thing as 1. So, Susan, actually, you divide by 1,000 and then divide by 10 to the negative 3. It comes out to 1. Now, my guess, Susan, as to why you're getting something so small is might have to do with how you're punching it into the calculator. So when you divide by 10 to the negative 3, or 10e negative 3. In your calculator, you have to enter it like this. Be 14 divided by 1000 times, open parentheses, 10e negative 3, close parentheses, equals. So, Susan, try entering this into your calculator, and when you do, I'm sure that it'll feed you an answer of 14. You just have to be very careful with parentheses and stuff when you're doing exponentials in denominators. That would be my guess. Okay, sorry. I just now saw that you got to the answer. Okay, so I'm all the way down. I'm on the last question in the feed. We finally made it to the bottom. Parthana, let's see. I didn't get what it is asking. When the decomposition reaction is complete, all the hydrogen peroxide has been decomposed, what substances other than oxygen remain in the generator? Oh, okay. Let's check this out. So, after the decomposition of H2O2 is complete. All right. So we have a reaction here. We have hydrogen peroxide. This is being catalyzed by manganese 4 oxide. It accelerates the decomposition process of aqueous hydrogen peroxide into water and oxygen gas. This equation isn't quite balanced as written, but now it is. So after the reaction is complete, we know oxygen remains, but they want to know what remains besides oxygen. And when you look, you'll have water. Water is a product of this decomposition reaction. And then the other thing that you have actually is MnO2. All right? And the reason why you have this left over is this is a catalyst, so it is not consumed. During the reaction, or by the reaction. So those are the two things other than oxygen. First, it's water. Second, your catalyst is still hanging out. So those are the two things you have left over. Awesome. Excellent. Alrighty. So even though it's not 5:15 yet, this is just a reminder and an announcement to anybody who's coming late that I will be away from my keyboard at 5:15. I have to drop my kids off to a thing. It's only 15 minutes from our house, so I'm going to be stepping out at 5:15 in about an hour. And then I'll be back around 5:30. I'm planning on extending office hours, so we won't lose any time. Oh, Carenza, you are welcome. Not Wilson. Welcome. So anyways, if you tuned in late, didn't hear that announcement at the beginning of office hours, I got to step out for about 15 minutes at 5:15, but I'll be back. We won't lose any time, etc. And we are, let's see, we're about an hour in to our stream, and the questions have started slowing. So let me know if and when there are any more questions. Out there. I'm not going anywhere, but I will start work on getting the homework problems for chapter 4 assigned in until new questions come around. Oh, new questions. Let's see. Part 3. Pre-question. It says that based on the information page 1, let me check that out. Okay, let's see. Part 3. In this experiment, all right, let's see what it says on page 1. Okay, so Carenza, here's kind of how I here's my 2 cents. So for the pre-question, it's a weird kind of category. So this is part 3. The pre-question. That part where it says based on page 1. I took a look at page 1, and the most relevant piece of information that I could spot was this: air is 21% O2, right? So, so if we had a bottle filled with air versus a bottle filled with pure O2, so this would be 100%. This would be 21%, i.e. about 1/5 the amount. So based on that, I would expect that 100% O2 would burn 5 times longer. It doesn't. That's not the case, but that's what I would expect. And there's a kind of logic to it. You can see, like, oh, well, there's 5 times as much, so maybe it'll burn 5 times as long. Turns out it burns hotter and faster and quicker. But that's based on the information on page 1. That would be my best. That's the answer that I think they're trying to lead us towards there. Let me know if that makes sense. I keep I'm like watching the replay. I keep hitting the table, which makes the camera bounce. Awesome. Okay, new questions. Okay, just wanted to make sure. Okay, so this is from Brianna. That I have the right idea on homework 2 when it gives elements like silicon 27. Let me just pull up homework number 2. Okay. Yes. Okay. Brianna, that is totally correct. So, in this nomenclature, it's always elemental symbol followed by the mass number. Right, which is the protons plus the neutrons. All the nucleons. Alright, so that is correct. And then when you're being asked to find the amount of protons in that element, yep, you can just go to the periodic table, because on the periodic table, you'll have silicon 14, and right up here, floating above every element, is Z, which is the atomic number, which is just the number of protons. You are spot on correct. Spot on correct twice over. Let's see, and if I wanted to find the amount of neutrons, yep. You got it. You are welcome. Let's see, how do we figure out what compound was formed? Okay, Susan, great question. All right, we haven't started talking about chemical reactions yet. We won't hit those for, I think, like chapter 6 or something like that. We haven't even started talking about ionic compounds. So, so whenever you are burning something, In other words, combustion. It's a reaction that adds oxygen to the fuel. So, magnesium plus oxygen will make, magnesium oxide. And honestly, Susan, you don't have to worry. I'm going to be grading this part very, very gently. Because, again, we haven't even started talking about ionic compounds. So you'd have no way of, knowing what type of ratio magnesium and oxide combine in. It just wouldn't. It's not within the scope of your knowledge based on what we've covered in class yet. So, magnesium will make MgO, magnesium oxide. Carbon will burn to make carbon dioxide. Let me just take a look at the other things they have in this situation. Iron will burn to make iron oxide. Oh, yeah, okay, they give, it's there, MgO, magnesium oxide. They give you the formula for it, so the equations that you're going to write are just going to be, they'll all kind of fall into this pattern. It'll always be fuel plus O2 makes fuel with oxygen. And they tell you all these compounds are given. In that table there, word equation, formula equation. You just have to write the fuel plus O2 and then it produces the product. Susan, great question. Where that 2 came from? Well, here, let me rewrite this equation. So our fuel, magnesium, reacts with O2 to make MgO, and this is something that we'll be talking about later in the semester. But you'll notice that on the reactant side, there's 1 magnesium and there's 2 oxygen, and on the product side, we have 1 magnesium and 1 oxygen. Well, we know that matter can't be created or destroyed, so we need our oxygens to match up. If we start with 2, we got to end with 2. So when we multiply this whole molecule by a 2, now we have 2 magnesium and 2 oxygen. The problem now is we have 2 magnesium on the product side and only 1 on the reactant side. So that's why we multiply the Mg by 2 to make sure that we start with 2 atoms of magnesium and 2 atoms of oxygen, and then we end with 2 magnesium atoms and 2 oxygen atoms. They always have to be the same number of atoms, of each atom, on both sides of the chemical equation. But that's something that we'll get to a little later. Again, I believe we'll get there in chapter 6. Why doesn't O2 become O4? Let's see. Let's see. Well, so O2 is a molecule two O2s means that we have two molecules of O2. O4 is a different molecule that is not involved in this reaction. So Susan, it's you never distribute the number. If you have, that's why you have two O2s, is because we have two different molecules of O2. O4 is a completely different thing that's not involved in any of these reactions. So that's why it's important to keep this number separated. Totally. Oh, no. You don't have to apologize. Yes, of course. You are welcome. And again, this is dealing with stuff that that we will get to a little bit later in the course, more around chapter 6. So we'll be dealing a lot more of this at that point. Oh, let's see. That is correct. Susan, that is... that is totally correct. And at this moment in time, I would totally not expect you to, like, know that, and I wouldn't test for that information at this moment. So you don't have to stress about those details, and that's also why they provide each one of those products for you in this lab exercise. Oh, let's see. Okay, Susan. So the product of this reaction is magnesium oxide, and this is a reaction that makes two of them. So 2MgO means 2 molecules of MgO are produced. Does that make sense? Yes. Yeah, totally. We're going to spend a long time in chapter 6 going over all of this. Oh, let's see. Corinne, I'm not sure if I already answered this, but for question 2, how do we determine the compound? So, Carinza, the exercise part 6 in that table under conclusion. So yeah, they give you the identity of every product form because there's no way at this moment in time that you would be able to determine what each product is. So all of those are provided in the table under experiment conclusion under the word equation part. They put it in parentheses. The identity of the product, and then every reaction. Let's see, I know I had it right over here. Is just is just right here. Fuel plus oxygen. Fuel reacts with oxygen to make fuel with oxygen. These compounds are given. There we go. You are welcome. Oh, let's see. Could I give an example of problem 9 on homework 2? Brianna, yes, I can. Let me see. All right, 2 naturally occurring. Okay. yeah, let me do something similar. All right, so let's see, this is homework 2, number 9. And this is not the exact problem, this is just a similar problem. All right, so let's check out this example. Okay, so number 9, let's see. All right, so here's, let's see. All right, so here's a problem similar. This one's actually a little bit harder than that one. Magnesium has 3 stable isotopes. Oh, that's isotopes. Isotopes. First, there is magnesium 24, magnesium 25, and magnesium 26. Magnesium 24 has a percent abundance of 79%. 25 is a percent abundance of 10.0, and then 26 is a percent abundance of 11.0. All right, and the mass of each the magnesium 24 is let's see, 23.985 AMU. Magnesium 25 is 24.986 AMU, and then magnesium 26 is 25.983 AMU. All right, and we need to determine the atomic mass. All right, so we need to determine the atomic mass based here. Hang on one second. Hey guys, you guys are doing. Sorry about that. Sorry about that. I am looking forward to the day where I can lecture and not have to ask my family to be quiet. Okay, so here's the these are the atomic the masses and natural abundance, percent abundance of each, and the question that we're being asked to solve is determine the atomic mass. Okay, so let's open up a new slide. So we need to take a weighted average here. So we need to take each mass and multiply it by its natural abundance over 100. So 23.985, 24.986. This will be times 10.0 over 100, and then 25.983. Over 100. All right. Now, oh, I may have closed out. There we go. All right, so we have 28 points. Oops. Not 28, 23.985 times 79 over 100. So this comes out to be 18.94815. Sig figs wise, we can only keep 3, right? So this will round to 18.9. Now for the next one, we have 24.986. And this comes out to be 2.4986. And here we can keep, again, we can keep 3. So it's 1, 2, 3. So this will round down to 2. That 8 rounds that 9 up to a 10, so 2.50 AMU after we round. And then for our last one, we've got 25.983 times 11 over 100 comes out to be 2.85813. And again, here we can keep 1, 2, 3 sig figs. So this rounds to 2.86 AMU. All right, so 18.9, 2.50, 2.86, and we add these all together. When we add them up, we get 24.26, but rules for sig figs and rounding, when you're doing addition, is we have to round to the least precise number, so we've got to round to the 10th place. So this will be 24.3 AMU. So that would be the answer for that would be the answer for this problem. And that is a very similar problem to the question that we see in problem 9. The only difference is problem 9, there's only 2 isotopes, whereas we have 3 in this problem. So it's a little more complicated. You do the exact same thing with problem 9, except, again, you only have 2 isotopes to worry about. Okay. All right. Okay, Aaron. Let's see. Apologies for joining late. Oh, you never have to apologize. Awesome. Gold. Or glad. Okay, Aaron. You may have addressed this. I actually haven't already. Oh, not Aaron. Sorry, Eric. Will post a. I will. I will refresh the link. Eric, they actually sent out an email. One of the faculty that did the recording said that they weren't really pleased with how number 4 came out, and so they re-recorded it, put a new video. So I think they took the old one down. Let me see if I have access for number 4. Okay, yeah, this one, yep, this was posted yesterday. Let's go to pages. Let's change this. Of course. All right, so the new link to the perfected video is now live on the Lab 4 page. So it should be good. If you go to navigate to the page, everything will look exactly the same, but I swapped out the hyperlink to the video, and so everything should be solid. Oh, dude! It was absolutely my pleasure. And you're actually getting an early jump on things for Lab Experiment 4. I'm almost ready with the upload for Lab Experiment 5. It'll probably be dropping today or tomorrow. So if you're an early bird type of person who likes to get a jump on things, it'll be available soon. Let me actually make a note of that. Alright, so that should be good. For any of you who joined in late, or not, there's no late to lab. I'm just here for 3 hours, but I announced this at a couple other places. Oh, dude. You too, dude. Have a rad rest of your Tuesday. For those of you who maybe tuned in a little bit after or didn't catch this announcement, I will be stepping away from the keyboard. That is what this cool little acronym AFK means. Ooh. But there's only one R in from. In about 6 minutes, there's a thing near our house that I just got to drop my kids off to. They've got a Tuesday activity that I got to get them to. So if you throw up a question during this time and nothing's happening, and you notice that that the board isn't moving and I'm not talking, and that here this little picture area, I'm gone. I will be back soon. I just got it. This thing is just a few minutes from our house. I just got to drop them off, and then I'll be back, and I'll be adding the time on to the end of office hours, so we won't be slighted out of any time together. So anyways, if you guys all will hang tight, I will return shortly. Feel free to add your questions to the live chat, and I will, as always, hit them in order of appearance upon my return. So we will be parted shortly, but I will be back. All right. Actually, I'm gonna bounce. I'm gonna bounce now. So actually, I'm gonna change this from 5:15 to 5:10. All right. I will see you all soon.
No. Come on. Get up. You gotta sit down.
All right, I have returned. All right, I'm back. Who's there and what's good? Let's see. In the absence of questions, I'm going to keep working on other class stuff, but I am back. I am here, and I am ready to take the question as they come. Oh, okay, sweet, Jen. Let's see. Dude! That's stinking rad. There's something about, like, I find, like, the rhythm that really kind of gets me in the mode of really zeroing in on a task or a thought. So yeah, I'm glad you liked it. There is plenty more Mastodon where Mastodon comes from. If you had to pick my favorite album is Leviathan. If you're looking for one place to start. Oh, heck yeah. Dude. Lo-fi and Tron, totally awesome study music. I find, especially if I'm, like, reading, putting on, like, lo-fi beats, is a really good playlist on Spotify that I'll use. But it's interesting. I find, like, with yeah, totally. I find with, like, electronic music and metal, they can have not all electronic is intense, but the rhythm section and the beats can be very, very rapid, and metal has that. It's just a dude on a drum kit. So anyways, they're very oddly similar. You never pick them as being similar, but as far as functioning as, like, study music, I use them both for that reason. What's up, Karenza? I'm here. I'm chilling, ready to take any questions that you guys have to dish out. Oh, let's see. Second to last question of Lab 3. Describe the desired effect. The 3 reactions that you observed. Okay. Parthana, let me check. Whoa. Oh. There we go. Okay, you said second to last question of Lab 3. So you're talking about oh, okay, I see now. You can pick any reaction you'd like to discuss as an example. Totally, the call's totally up to you. let's see. You know that we are all the faculty are collaborating on. Oh, of course, you are welcome. Oops. There we go. All the faculty teaching this summer are collaborating on writing the quizzes, and one of my colleagues just finished the quiz 5, so I need to take a look at it just to make sure there's no typos or errors, and that should be going live relatively soon. Oh, and oh, let's see. Could you go over question 12 on homework 2? Absolutely can. Ah, Jen. Chem 400 is first semester Gen Chem. OChem is 420/421. They usually have me teaching Chem 400. Sometimes I get to teach Chem 420 lab. Usually the full-time faculty teach the OChem sections. Because they are the most fun. Okay, here, hang on 1 second. Okay, what was it? It was number 12? Oh wait, hang on. Cancel. Homework 12. Homework 2, question 12. Let's see. Ah! Ah! Brianna. Great question. Actually, homework 2, question 12, I'll answer homework 2, question 12. At the beginning of lecture tomorrow. Brianna, that question is literally where we're going to be starting lecture tomorrow. So I'll save it for then. So stay tuned. Hopefully you can live with the suspense. Okay. Prathana, let's see. Does it mean chemical reaction? Let me take a look at the problem. Oh, let's see. Boop. Yes, Parthana. You can start and stop the homework anytime before the due date. At Peyton, that is awesome. Yeah. We get to party 2 semesters in a row. And Peyton. So honestly, OChem is hard, but it is also rad. Like the coolest class I have ever taken or taught in my life. OChem is amazing. Definitely challenging, definitely difficult, but the thing is Gen Chem, Chem 305, Chem 400, Chem 401, it's like topic. Here's a topic. We learned it. Here's a topic. We learned it. Here's a topic. We learned it. With OChem is predicated on this very simple premise that if you can understand the structure of a molecule, you can predict its reactivity. And the entire 2 semesters is a meditation on that principle. Understanding structure and using structure to predict the reactivity. Now, it is super hard. And yeah, Brianna, your calc teacher told you that OChem made her switch majors in college. There are terrible OChem teachers out there. And they can definitely ruin it for people. Also, OChem is very, very visual. Gen Chem tends to be very math heavy. There's almost no math in organic chemistry. Organic chemistry is about visualizing things in 3 dimensions, understanding shapes and how they interact. Dude, yeah, that's what you gotta do. Brianna, organic chemistry has ruined a lot of lives. Mine included, actually. When I was fresh out of high school, in high school I was good at math and science, so I had people in my life telling me, like, oh, you should go to med school. You're good at math, you're good at science, you should be a doctor. So I'm like, okay, I guess I'll be a doctor. And so I was pre-med. And if you're pre-med, you have to take OChem. And I was terrified. I was terrified of this class, like I was for no other class I'd ever taken, because it has such a reputation. Like, its reputation is, this is the course doctors fail, right? This is the course that doctors find hard. And so I studied like I'd never studied before. Like, I was reading ahead of time. I was doing every single problem, all the problems I could find, like, take no prisoners, just like, it was intense. And I realized two things. As long as you stay on top of it, as long as you don't fall behind, it's not as bad as people say it was. It's not as hard as people say it is. As long as you don't fall behind, as long as you stay ahead. If you can do that, it'll be hard, but it won't be the thing you're afraid of. The second thing I learned was that it was awesome. Like, awesome. Like, the coolest stuff I had ever seen. And I fell in love with it. And I changed my major from being pre-med to being chemistry, and that's how it ruined my life. Because if I had stayed pre-med, I could have been a doctor. I could have been making bank. And because I fell in love with organic chemistry, I am YouTubing from my office as a part-time faculty at Folsom Lake College. Which I'm happy to be at Folsom Lake College, by the way. And hopefully one day I'll be full-time somewhere. Maybe here, maybe elsewhere. I'll never make what a doctor makes. But I love my job, and so, you make trades. You trade for stuff. Are there sig figs in OChem? Not really. A little bit in lab. But not much. Oh! Thank you. That is sweet of you to say. Yeah, I do love what I do. Right now I'm teaching like Chem 305 and Gen Chem and stuff, because when you're part-time, the full-time faculty take the fun classes. I used to be full-time at a college in Southern California. I had to make a move for family reasons, so I got to teach organic chemistry down there. It was awesome. Right now I'm doing the Gen Chem thing, but eventually when I get full-time somewhere, I will I'll be teaching that sweet OChem again. Because it is a blast. It is a blast to take. It's a blast to teach. And one cool thing here is usually spring semester they let me teach Chem 420 lab, so I do get to teach a little bit of OChem up in here. Yes, you will. Yes, you will. Where's my mouse? There it is. Totally will. No way. No way. We're at. So I grew up in Temecula. It's like an hour north of San Diego. Oh, let's see, Eric, you're back with the question. Let's see. One more question for you. For lab for part 2 and 3. Okay, let me just start by opening up. All right, lab 4. 2 and 3. Part 2 and part 3. Dude, no way! You're best friends from Temecula? I was born in Long Beach, but I grew up there. And Carenza, I totally know Orange County. I went to UCI. So yeah, I totally hung out in Dana Point, Laguna Beach. Those are like my old college stomping grounds, and now I can actually say old. That's weird, Eric. There's a decent chance that that I might know your friend, or we might know people who hang out and stuff. That's super weird. Okay, sorry. You have an actual question. I got distracted by your best friend being from Temecula. Okay, let's see. The video doesn't give us the masses of an empty crucible. Okay, totally. If okay, so this is at Eric. So if the video is missing certain data points, totally don't sweat it. Oh, bro, yes. That is a long drive. My wife is from up here. She lived in Folsom, and we actually met online, and so I drove up to meet her, and then we started long distance dating. So I've done that drive so many times. Oh my gosh, that's awesome. Yeah, so you know Aldrich Park in the center of UCI's campus, and they have all those beautiful magnolia trees. I used to climb them and do my homework up in there. All right, Tatiana, we've got questions. Okay, let's see. Lab 2, question 3. Let me pull up Lab 2. Calculate the mass of a quartz of mercury, and they give the density. Okay. Great question. So, let's look at some units. So, oops. So this is lab 2. Question 3. All right, so we're given that the volume of mercury is 946 mils, and the density, mercury we're told, is 13.6 grams per mil. And we also know that density is mass over volume. So our mass is going to be equal to our density times our volume. Now, you plug in density, 13.6 grams over milliliters. You multiply that by 946 milliliters. And here, milliliters cancel. So, Tatiana, as you already know, when you multiply these two numbers together, it gets outrageous, right? This gives us a mass of 12,865.6 grams. And we can only keep 1, 2, 3, 1, 2, 3. They both have the same number of sig figs. We can only keep 3 of them. So here's the thing. This has to keep right here. They have to have the same place value. All right, we got to have the same place value here and the same place value here. So if we left our answer at 129, its place value would be the ones place, but in our original number, it's in the hundreds place. So we need to add 2 zeros so that it keeps the same place value. So the answer here would be 12,900 grams, or if you wanted to convert to kilograms, you could write this as 12.9 kilograms. But again, that's a different unit. If you're staying in the units, if you're staying in the unit of grams, then 12,900 is the same. Just remember, whenever you round these right here, turn into these. They become zeros. Does that make sense? Calculating AMU, why put the percentages over 100? Okay, awesome, Tatiana. I'm glad that works. So Carenza, whenever you have a percentage, like oh wait, hang on, there we go, like 88%. When you divide it by 100, this is just how you convert a percent to a decimal. So you divide by 100 to convert that percentage to a decimal, and you have to convert percentages to decimals before you multiply them by numbers. But here's the cool thing. This 100 right here is based off of a definition, which means that it's exact, not measured. So that 100 will never limit your sig figs. You always roll with however many sig figs are up in your percentage. But that 100 in the bottom is just based off a definition, so it'll never hold you back. It'll never restrict the number of significant figures you can have in your number. Oh, thank you. Oh, let's see. Homework 2, number 9. Let me take a look. Let's see. Don't see the answer as an option. Done the problem a few times. Okay, here. Hang on one sec. Let me check it out. All right, let's... Okay. Wait, let me just... Okay. Yo. So I just double checked the math. Wait, let me make sure it's at homework number 9. Yeah. And the correct answer is present. It is definitely there. Totally. Yeah, no worries. I know sometimes it's just reassuring to just to know that there's not a mistake. You definitely are in the right place. Okay, let's see. Could you show me a problem like it? So I can see where I may have gone wrong. Yes. Yes, I can actually. Here. Whoa. So here's a problem that is the same type of problem, just with different numbers. Here we will be doing it with magnesium, which for whatever reason has been a popular element today. So magnesium has 3 stable isotopes. There's magnesium 24, whose percent abundance is 79. Oops. Whoa, how's that for ugly? Percent abundance is 79.0, and whose atomic mass is 23.985. We have magnesium 25, whose percent abundance is 10%. Oh goodness, where'd my live chat go? Wait, hang on. There we go. Magnesium 25 is a percent abundance of 10%, atomic mass of 24.986, and magnesium 26, whose percent abundance is 11%, whose atomic mass is 25.983. All right. So here's the info. Let's go ahead and solve and find our atomic mass. So we need to take each mass and multiply. So for magnesium 24, its atomic mass was 23.985, and we'll multiply by its percent abundance, 79.0, over 100. We're going to do the same thing for magnesium 25, its atomic mass, 24.986 AMU times its natural abundance, 10.0 over 100. And then we do magnesium 26. Sorry, whose atomic mass is 25.983 AMU. And we multiply here by our percent abundance over 100. All right, so now we need to multiply each of these. When we multiply by for magnesium 24, our calculator gives us a value of 18.94815, but we're only allowed to keep 3 sig figs. So when you count them off, 1, 2, 3, that comes out to be just 18.9 AMU. When it comes to magnesium 25, right, with 24.986, you multiply this by the percentage divided by 100, comes out to be 2.4986. And again, we can keep 3 sig figs, 1, 2, 3. That 8's going to round up, so this will be 2.5, but then we still have to have 3 sig figs, so 2.50 AMU. Finally, when we multiply 25.983 by the percent abundance of magnesium 26 divided by 100, here we get 2.85813. Our percentage here, our natural abundance, has 3 sig figs. We can only keep 3 sig figs, so this will come out to be 2.86 AMU. Now we're going to take all 3 of these and add them together. All right. When you do that, they sum to 24.26 AMU. But now we have to use the rules of sig figs for addition. our least precise number is precise to the first decimal place, so we have to round to the first decimal place. So our final answer here will be 24.3 AMU as our final answer with the correct number of significant figures. So hopefully, okay, let's see. Okay. Okay, right. So far, for problem on homework 2, first time goes with 17. Yep, and the 17. So 75. Let's see. Remember, it's 75.00%. And it goes with 21.30 AMU. So there it is. Yes. Yeah, 21.30. Yeah, okay. That had to be crazy frustrating. You're like, every time I'm multiplying it through and I'm like not seeing the correct answer. I bet if you go back and do it with 21.30, you'll hit the right answer. Heyo. This is what office hours are for. This is exactly what office hours are for. And I guarantee you, you'll remember this type of problem. You will do well on this type of problem, and you'll be dialed into the details the next time you run into one of these. Dude, well done. It's my pleasure helping. Alrighty, well, I think we've, it is now 6:20. I think that I'm going to put a pin in office hours for today. It's been awesome. As always, thank you everyone for coming out, hanging out, and I will see you all tomorrow at 1:20. We'll hit up. What are we going to talk about? Electron configurations and the D block. So stay tuned, stay safe. I will catch you all on the flip side.